Hi everyone, my name is Rachel Oliver. I'm a Professor of Materials Science at the University of Cambridge, and I'm interested in my research in light emitting diodes, or LEDs. LEDs are a really fantastic technology because how important they are for energy saving. Now, right now, it's quite cold in Cambridge where I live, it's quite dark, and I've got the lights on at home pretty much all the time, and that's burning a lot of energy. If we look at all of the electricity generated across the world, then actually about a quarter of it is used for lighting. So that's a huge fraction of the world electricity generation just goes into lighting up our homes and our workplaces and all the places we go. So we really do need technologies which can reduce the energy cost of lighting. And that's why light emitting diodes, LEDs, are so fantastic. So this is a quote from the Climate Group, who are trying to improve the sustainability of our technologies. They say that a global switch from current bulbs to energy efficient LED technology could save 1.4 billion tonnes of carbon dioxide every year and avoid the construction of 1,250 power stations. So these are massive savings in greenhouse gases, massive reductions in energy usage. And it's all down to these tiny little light sources called LEDs. And what we're going to do in this talk is get right inside an LED light bulb and find out what's going on and why we're managing to save so much energy. Okay, so what is inside an LED bulb? Well, this is a fairly typical LED bulb that you might be able to buy, say in John Lewis, for example, any shop you like, really. And we bought this one in John Lewis before we took it apart. And then what we've done here is taken off this kind of plastic cap, which is the diffuser. It's just there to help spread the light out. And underneath we find another thing, looks a bit like a ping pong ball, but it's not just a normal plastic ball. It's actually made of a material called a phosphor. And what a phosphor does is it absorbs light in one colour and then emits light in another. So that's not the bit that actually makes the light. If we look under the phosphor cap, we see the actual light emitting diodes, the LEDs, which are what is going to give out the light. And what we can see here is that inside the LED bulb, we have these bright blue light emitters. So our LEDs in our white light bulbs are actually giving out blue light. You can't really tell it's blue in this picture because it's so bright, it's saturated the camera and it looks white. But here you can see the blue light, and then when we put the yellow phosphor on top, it absorbs some of the blue and gives out yellowish light, and the two together give us something which looks white. So that's the first thing, that all the LEDs used in these bulbs are actually giving out blue light. Let's drill down. So we've seen what's inside the bulb, and we've got these blue emitting LED chips, but what's inside those chips? Well, we can actually see there are multiple light emitting diodes on the PCB, or printed circuit board, inside the bulb. And if we zoom in on just one of those, this is what we might see. We've got this chip here with a sort of polymer dome over the top to protect it, and then contacts going out to the outside world. We're going to zoom in even further. Now we can see this metal on the top, and there's two different layers of metal giving electricity to different layers within the LED device, and they're labelled as P and N electrodes, those layers of metal, for positive and negative. So there's going to be a positive and a negative side to the device. But we still can't really see the light emitting material. We're going to have to zoom in even further. So rather than just imaging under the optical microscope, what we're going to do next is take a section of that LED and have a look at it in a scanning electron microscope, or SEM. Now to start with, that doesn't really show us a lot, but then what we've done here is we've literally dug a hole in the surface of the LED. We did that with a focused ion beam microscope, where ions crash into the surface and knock away part of the material. So now we can zoom in still further. So now finally we can see the light emitting material here. This layer here is gallium nitride, which is a synthetic or human-made material, isn't found in nature at all, which has been made to give out blue light. And we've got the metal layers above and below it, which are going to get electricity into those layers, which are labelled P and N. and we'll talk a bit more about positive and negative charges in semiconductor materials in a moment. But we still actually can't see the real light emitting region. We're going to have to zoom in still further. So I'm going from a scanning electron microscope image to a microscope with even higher resolution. And here I'm in a transmission electron microscope image. And you'll see my scale bar is now in nanometers. So a billionth of a meter is a nanometer. And we can now see we've got various layers of different nitride materials in our LED. But the most important bit is this bit I've labelled MQW, which stands for multiple quantum well. And these multiple quantum well structures are layers of a material called indium gallium nitride, which is just gallium nitride with a bit of indium added. And they're only a few atomic layers thick, maybe typically about 10 layers of atoms thick, which means about 2.6 nanometers in thickness. And it's these really tiny, incredibly thin layers of indium gallium nitride that actually give out the light. And to understand what they do and why they're so important, we're going to have to talk a bit about how semiconductor materials work and about how electricity moves through different materials and why semiconductor materials are kind of special. So here we are inside an LED. We've got a simplified version now of the structure I showed you on the last page. We've got our semiconductor material, to which we have an N contact and a P contact. We're going to use those to inject positive and negative charge carriers. Maybe that's already starting to sound a bit funny. We're used to electricity being carried through conductors on negative charges, electrons. So what are these positives I'm talking about? So let's think a little bit about conduction. So we're used to conductivity in a metal. Metals conduct electricity under pretty much any circumstances. So in my very simple circuit here, when the switch is closed, electricity flows through the metal and the light bulb comes on. And we understand a bit about what's happening in metals. The metallic bond is like a sea of electrons which are all free to move throughout the metal structure and carry a current. So hopefully that's familiar to many of you. And you should also, I suspect, have heard about insulators. In insulators, even when the switch in my circuit is closed, the light doesn't turn on because no electricity flows through the insulator. And that's because in an insulator, all the electrons are bound up in either ionic or covalent bonds. They're fixed around the positive ion cores, and basically they ain't going anywhere. So a semiconductor, well, that semi tells us that it's something in between. When we close the switch at room temperature, we may not see current flow. At low temperature, no current flows. But if we heat up the semiconductor material, then a current flows. In the semiconductor, if we provide some heat, some thermal energy, then some of the electrons, which in our insulator were in bonds, they can escape from those bonds and move through the material. And you can see that when they do, they leave behind gaps in the arrangement of electrons around the ion cores. And electrons that are still in the bonds can actually hop over into those gaps. And as we watch it, it's as if the gaps themselves are moving through the crystal. We refer to those gaps literally as holes. And we think of holes as having a positive charge because a negative charge has been taken away from them, leaving a positive behind. And we think of them as actually being a secondary type of charge carrier that can move through the material and carry the current. So in semiconductor materials, the current can be carried either by negative electrons or by positive holes. The movement of holes through the material is a bit like this puzzle. So in this puzzle, we're actually moving the tiles around to try and order them into numerical order. But what we can think of moving around is this one brown gap in the puzzle, which allows the other tiles to move. And that's like the hole, the positive charge moving through the semiconductor crystal. Okay, so we've got our LED and it's got our semiconductor, and we can see that in our semiconductor material we can have holes, positive charge carriers carrying the current as well as negative electrons. And it turns out that if we change the composition of the material very, very slightly, we can cause it to either have lots of holes, and that's what we call the P-type material, or lots of electrons available to carry the current. We call that N-type material. And we send in the electrons from the N side into this region labelled quantum wells, and the holes from the p side, and when they meet up, they combine with one another, and that's why light's given out. Now, what's important about that is that the combination of electrons and holes is naturally a light-emitting mechanism. When the electron meets a hole, it loses energy, and that spare energy is given out as light. It's not like an old-fashioned light bulb where you have a long filament of metal, and in order for that filament of metal to have to give out light, it has to get really, really hot. And the heat then, the excess heat in the material, is effectively emitted as light. It's just kind of an accidental byproduct of heat production. And so you need a huge amount of heat before you get any light at all, and it's really inefficient. Here, we don't need to emit any heat whatsoever. The combining of the negative and the positive charge, the electron and the hole, naturally gives out light without heat having to be emitted. So the device can be really efficient. So that's all great, but what are these thin layers, these indium gallium nitride quantum wells for? Well, we're going to have to learn a bit more about semiconductors to explain that. Now, many of you will be used to the idea that different elements have different energy levels. Okay? We know that there are different shells in which there are spaces for more or less electrons, and also that the energy levels of those shells differ between different elements. Many of you will also be familiar with the idea that electrons can be in the same energy state in pairs, but it's not okay to shove a third one in. You may have met the Pauli exclusion principle, which basically says you can have one spin up and one spin down electron in each energy state, and that's it. There's no space for any others. So what does that mean when we start to build a material out of many, many atoms? Well, we start with one atom which has its energy levels. And when we come to have two atoms together, well, we can't have 4 electrons, for example, in exactly the same energy state. That just doesn't work. So the result of forming the bond in the molecule is to split the available energy levels and make extra energy levels. If we add on more atoms, we get more energy levels, so that once we've got a few atoms in our molecule, the energy levels get quite close together. And if we think about something like a crystal with millions and billions of atoms, then the energy levels become so close together they merge into one, and they create what we call a band. So within that band, electrons can take pretty much any energy they like. But we end up, just as there are gaps between the energy levels, significant gaps between energy levels in a single atom, there are different bands with gaps in between them. And we call those gaps a band gap. So in the bands, electrons are allowed, but in the band gap, that's an energy level that the electrons can't take. It's an energy that's completely forbidden. Now that sounds really weird, but actually we're used to there being energy states that things can and can't have. Okay, so if you imagine me standing on a chair, okay, stood on the chair, I am completely stable, I am in an allowed energy state. I can step down on the floor. I'm there, I'm also completely stable. I can stay stood there, I'm in another allowed energy state. But what I can't do is jump off the chair and expect to kind of hover in the air midway between the chair and the floor. I'm not stable in that state. I'll fall to the ground. It's just the same thing here. The electrons are in a stable state in this band, they're in a stable state in this band, but anywhere in the middle, they're just going to go down to this lower band down here. Now, in metals, okay, we do have bands. The important thing is that those bands are not full of electrons. Their bands have some space in them, some gaps. And because the band isn't full, there's space for the electrons to shuffle around and move. And that shuffling around of the electrons allows the current to be carried. And that's true at high temperature, at room temperature, or indeed at low temperature. However, in an insulator, the lower energy band we're showing down here is full. And then there's a big, big, big gap in energy to an upper energy band up here. And even when we heat the system up, there's not enough energy available for electrons to make the leap across that huge gap to be able to carry the current. So at high, low or medium temperature, we still have no electrons in the upper band, and the bottom band's completely full, so there's no space for the electrons to shuffle about. In a semiconductor, however, the gap is much, much narrower. So when we do heat it up, electrons can leap across the gap, and then the electrons in the top band can move, and the holes left in the bottom band, they can also move. So we call the two bands then the conduction band and the valence band. The valence band is just like the band that's to do with bonding. It's where the electrons sit when they're stuck in their bonds. And when they're promoted across the band gap, they're pushed across the band gap by some thermal energy, then when they're up there, they can move and carry the current, and they leave behind holes in the valence band. So I've now moved an electron up from my valence band into my conduction band, leaving behind a positive hole. And what we find is that electrons are like footballs. So footballs roll downhill, and electrons tend to always find their way to the bottom of the conduction band if they're in the conduction band. But holes, they're not like footballs. They're like helium balloons. They tend to float up to the top of the valence band. So our electron and our hole sit at the band edges, like I'm showing here, and the amount of energy that's given out when the electron drops down from the conduction band into the valence band to combine with the hole is given by the energy difference across this gap. And that amount of energy relates to the colour of light we get out. And really, really narrow band gap would give us red light, bit wider would give green, quite wide would give blue, very wide would give us something out in the ultraviolet. So the band gap defines the colour of light that the semiconductor LED might emit. Now, different materials, different elements, we said, have different energy levels, and different semiconductor materials have different band gaps. Indium nitride has a much lower, much narrower band gap than gallium nitride. And in our LED, we use indium gallium nitride, which is just a mixture of indium nitride and gallium nitride, actually. And that has a kind of in-between band gap, and it actually has a band gap that's just right to give light emission in the blue, which is what we saw in our LED light bulb. Now, in our very, very tiny thin layers of indium gallium nitride that are sandwiched between these barriers or layers of gallium nitride, that gives us a region of lower band gap. And as I said, the electrons like to fall down. Imagine you rolled a football along this landscape. It would fall down into this kind of bucket made by the lower conduction band edge. So the indium gallium nitride makes a bucket for electrons, and for the holes in the valence band, which like to float up like helium balloons, it's a bit like catching them in a sort of top hat structure just there. So the electron and the hole are trapped together in this very, very narrow space. And that makes it much more likely they'll meet one another combined, much more likely we'll get lots of light out of this device. If we didn't have these narrow layers, then the electron and the hole will be together in a really large space, and they might not meet, and they might wander off and be lost somewhere or recombine in another way which didn't give out light. It's a bit like if I said to one of you, let's meet up, and you said where, and I said Cambridge. Well, we could wander around the whole city for like the whole day and never find each other. But if you said, let's meet up, well, where? We'll meet in central Cambridge at the market square by the fountain. Well, we've confined ourselves into quite a small volume, and it's quite likely we would meet. And that's what we're doing. We're squishing the electron and hole together in a small space to make them likely to meet. When they meet, the electron falls down from the conduction band to the valence band, and light is given out. And that's really important to making our LEDs as efficient as possible and not wasting any of our energy, squeezing the electron and hole together in that same volume. Okay, so there we've learned quite a lot about what's going on inside an LED. And if you want to learn more, there's lots of resources available on the website from my research group, which is the Cambridge Centre for Gallium Nitride. You can just search for that, or the web address is here along the top of the page. What you can find in our resource section of the website is linked to our YouTube channel, where there is a whole longer video of me giving a much more extended version of this talk. It's about 45 minutes or so, and it delves more into the kind of research we do in this field. If you want to learn more about the fundamentals, you could also download our app from Google Play. It works on Android devices, and you can search for it on Google Play using the search term LED Lab, or again, link to it from the resource page. Anyway, I hope you enjoyed hearing about some of the materials I work on, and that you have a great day learning about other materials as well. Okay, thanks. Bye.